Hi, today I'll be talking about my ECE 570 final project, which was based on a 2021 ICCV paper, which built a new unsupervised pre-trained model specifically for the domain of remote sensing. And I extended that paper by testing out the model to test its robustness on different resolutions that the paper did not touch on. So as far as background, just so everyone understands, remote sensing is basically the field where we have sensors in space and we use it to measure various characteristics on Earth. Common applications are tracking yield of crops over time, or classifying land cover, or detecting objects on Earth. Obviously, remote sensing generates a huge amount of data, and so labels are scarce, and therefore an unsupervised pre-trained method is key. And the authors also point out that there is a domain gap between today's pre-trained models, which have primarily been trained on datasets such as ImageNet or CPR10, and where the remote sensing industry needs to go. And really quick background on the architecture of the model. Basically, we end up taking many remote sensing images, apply various transforms to them, create latent representations of them, and then end up projecting those latent representations into different subspaces here on the right side that are variant or invariant to the different transforms. And using the author's pre-trained method and building a classifier on top of it, the authors do empirically show that there is in fact a gap between today's pre-trained models and their method specific for remote sensing data by having a higher classification accuracy on the remote sensing task. And so I build upon that first by implementing the original paper, which was mainly done by using code provided from their GitHub. And then I extended that with two new experiments. I wanted to test the robustness of their pre-trained models to data sets that were not used in the author's experiments. So namely high resolution data, about 0.3 meters per pixel, whereas the author's experiments were done on data that was about 10 meters a pixel, so about 30 times higher resolution. So I extended it with a classification task on top of a high resolution data set and a classification task on a high resolution data set with noise. And so this all resulted in two new Python files, one which leveraged the pre-trained model and ran a new classifier on top of the high resolution data set, which in this case had 21 classes instead of 10 classes as in the author's experiment, and also code to go through the data set, through the directories, parse out the tensors, and then the labels for that new data set and plug that into the machine learning model. So all in all, there was code written to parse through that new data set, split it into training and test, adjust the fully connected layers for the classification task to account for the new number of classes in the high resolution data set. Also had to adjust the transforms in the data loaders because the high resolution data set had a different size than the original data set, and also I wrote code to add noise and also to plot the results. So overall results, we noticed that for the classifier on high resolution data, using the non-noisy high resolution data set, ImageNet pre-trained model, and then building a classifier on top of that actually had better results, which is counterintuitive to what we would have expected with this paper. However, when we added noise to the data, the author's method was actually a better avenue for doing a classification task. So overall, what does this tell us? The pre-trained model from ImageNet did better on non-noisy data. The noisy data did better with the author's method. Both experiments did worse on the high resolution data. And this is likely because the pre-training method specifically learned representations of only low resolution data. So a future avenue for experimentation can be experimenting with fine-tuning the last layers of the unsupervised pre-trained method that the authors developed to potentially learn better representations of the high resolution data and then run those experiments again. All right, thank you.